Hello, in today's video, I'll be solving questions on A2 Electrochemistry from October-November 2019, paper 4-2. Question 1. An electrochemical cell is constructed using two half cells, a Br2/Br minus half cell and an Mn3 plus/Mn2 plus half cell. A. State the material used for the electrode in each half cell. When we have a non-metal/an ion half cell, platinum is the electrode. The same way, when we have an ion/an ion half cell, platinum is the electrode. So for the non-metal/ion half cell, the ion is in solution and the non-metal is directed through this opening onto the platinum plate. If you have an ion/an ion half cell, the two ions will be in solution and then the platinum wire is dipped inside the solution. So the electrode for these two will be platinum and platinum. B. The cell is operated at 298 Kelvin. The Br2/Br minus half cell has standard concentrations. The Mn3 plus/Mn2 plus half cell has the Mn3 plus concentration at 0.5 mole per decimeter cube and the Mn2 plus concentration at 0.1 mole per decimeter cube. I. Use the next equation to calculate the electropotential of the Mn3 plus/Mn2 plus half cell under these conditions. So to calculate the next equation, we use the formula. The electropotential of a non-standard half cell, E, is equal to the electropotential of the half cell under standard condition plus 0.059 over Z. The Z is the number of electrons transferred in that half cell, log concentration of oxidized species over the concentration of reduced species. From the data booklet, the Mn3 plus to Mn3 plus half cell equation is given as this. The electropotential value for this equation is plus 1.49 volts. So our E is equal to 1.49 plus 0.059 over the number of electrons transferred in this equation is 1. So over 1 log concentration of oxidized species. This is the oxidized species and the concentration is 0.5. So 0.5 divided by, this is our reduced species, the concentration is 0.1. So you have 0.1. And so the electropotential of the non-standard half cell is equal to 1.53 volts. II. Calculate the E of cell under these conditions. The electropotential of the cell can be calculated by adding the electropotential of these two half cells together. And to do that, we can see that the electropotential of the Mn3 plus to Mn2 plus half cell is more positive than this value. We got this from the I above because this is the non-standard half cell. So we calculated this in I above. And so since this is the positive pole, reduction occurs at the positive pole. And we can see that this equation is already undergoing reduction. So you have to maintain the electropotential value as 1.53 volt plus the electropotential of this one, of course, is less positive. It means that oxidation will be occurring at this half cell. So it means that you have to reverse the sign of this electropotential value. And so that will be negative 1.07 volts. And this gives us 0.46 volts. I. Write an equation for the overall cell reaction that occurs. To do this, we add these two half cells together. But we first of all have to make sure that the number of electrons in these two equations are equal. And so since this is 2, we have to make sure this is also 2. So we multiply this whole equation by 2. And so it means that we get 2mn 3 plus 2a minus given 2mn 2 plus. And we maintain this equation as Br2 plus 2a minus given 2br minus. Now again, if you look at the electric potential of the Mn3 plus to Mn2 plus half cell, it is more positive. It means reduction should be occurring at this half cell. And since this equation is written in the reduction form already, it means that we have to reverse this other equation, the Br2 to Br minus equation, since this will be the one undergoing oxidation. After reversing this half equation, we can now add the two half cells together to form a complete cell. So we get 2mn3 plus 2br minus plus 2a minus giving 2mn2 plus br2 plus 2a minus. We can also see that the number of electrons at both sides of the equation are equal, and so we can cancel them out. So it means our final cell equation is 2mn3 plus 2br minus giving 2mn2 plus br2. C. An aqueous solution of copper 2 sulfate is electrolyzed using copper electrodes. A current of 1.50 amps is passed for 3 hours. 5.09 grams of copper is deposited on the cathode. The charge on one electron is negative 1.60 times 10 power minus 19 coulombs. The relative atomic mass of copper is 63.5. Use this data to calculate an experimentally determined value for the Avogadro constant, L. Give your answer to 3 significant figures. To solve this question, we use two equations. The first equation is Q is equal to IT. So this is the quantity of charge, current, and time. And this is equal to the mass of copper deposited. So that will be M. The current is given as 1.5 amps times the time, which is 3 hours, but we convert 3 hours to seconds. So 3 times 60 times 60 will convert the 3 hours to seconds, is equal to the mass of copper deposited, which is 5.09 grams. We get 16,200 coulombs is equal to 5.09 grams. This is equation 1. Now, Avogadro's constant L is equal to charge on 1 mole of electron over charge on 1 electron. The charge on 1 electron has been given in the question as negative 1.60 times 10 power minus 19 coulombs. But we don't know the charge on 1 mole of electron. The charge on 1 mole of electron is the same as 1 Faraday. And to calculate 1 Faraday, we need a second equation. To write the second equation, we first of all need to consider the copper half cell. So you have Cu2 plus 2A minus given Cu. We know that 1 Faraday is equal to the charge on 1 mole of electron. But in this equation, there are 2 moles of electron passed. So it means that we are dealing with 2 Faradays in this equation. And this 2 Faradays is equal to the mass of copper deposited. To calculate the mass of this copper, we know that amount is equal to mass over molar mass. And so the mass of the copper is equal to the amount times molar mass. The amount is 1 mole, so it is only 1 mole of copper that is deposited per this equation. So that will be 1 mole times the molar mass. The molar mass has been given as 63.5. So 63.5 grams per mole. It means that the mass of copper in this equation is 63.5 grams. So we have gotten the mass associated with the 2 Faradays as 63.5 grams. This means that per this equation, 2 Faradays is equal to 63.5 grams, and this is our equation 2. Now we can use ratio and proportion on equation 1 and equation 2 in order to find 1 Faraday. If we cross multiply, we get 2F times 5.09 grams is equal to 16200 times 363.5. And so we divide through with 2 times 5.09. Divide this also with 2 times 5.09. So we cancel this out, and once we do this, it means that we now have 1 Faraday. So 1 Faraday is equal to 101051.1 coulombs. This is the charge on 1 mole of electron, and we said our Avogadro's constant is equal to charge on 1 mole of electron. So 101051.1 divided by charge on 1 electron, which is 1.6 times 10 power minus 19 coulombs, and that gives us 6.32 times 10 exponent 23. D. Explain why magnesium metal cannot be obtained by the electrolysis of dilute aqueous magnesium sulfate. Your answer should include data from the data booklet. So to solve this question, we need to consider the two equations. Mg2 plus 2A minus giving Mg. The electropotential value for this half cell is negative 2.38 volts, and 2H plus 2A minus giving H2. The electropotential value for this half cell is 0.00 volts. Now we can see that the hydrogen half cell is having a more positive electropotential value. It means that this half cell is the one to be undergoing reduction, and so for that matter, there is no way Mg2 plus can undergo reduction to give Mg solid. So after writing these two half equations in the electropotential values, we need to conclude that hydrogen is produced instead of magnesium. Thank you for watching. Please subscribe to this channel. See you in the next tutorial.